Alright, this is going to be the final chapter of the electricity sector. Alright, looking at this question here, what do they want? A simple DC electric motor is fitted with a coil that rotates in a magnetic field. A commutator connects to the power supply of the coil. What is the purpose of this commutator? Now guys, always remember that in a DC motor, guys, DC motors are actually using split rings. And split rings, they only have one specific purpose. It is to rotate the direction of current every 180 degrees so that the coil may continue to spin in 360 degrees. So look at this answers here. Convert AC into DC, absolutely not possible. It prevents the current from becoming too great. It is absolutely not possible. It reverses the direction of the current in the coil after every 180 degrees rotation of the coil. This is the absolute answer here. Then looking at the next question here, what is the purpose of a relay? I've mentioned this as well. You will always see this in your paper 2 question. In short, a relay is basically using a small current to control a large current here. So to change a large voltage in a small voltage, no. This is a transformer, right? To change a small voltage in the large voltage, no. To use a large current to switch on a small current, the opposite. To use a small current to switch on a large current, yeah guys. So D is the answer here. Which device uses a split ring commutator? A DC motor definitely uses a split ring commutator. AC motor uses slip ring commutators, yeah guys. Alright, in which device is a split ring commutator used? Obviously it's going to be a DC motor. To reverse the direction of current, to change the direction of current in the coil as it turns. No other logical answer here. Alright, so C is the definite answer here. Moving on to the next part here. A bar magnet is made of a metal. Suggest a metal from which the bar magnet is made of. There are 2 options only, right? Either you use steel or iron. But for a bar magnet, it is always going to be steel because it is considered a hard metal. I've mentioned this many times in class already. Alright, then figure 8.1 shows the bar magnet being inserted into the coil of the wire. The N pole and south pole of the bars are marked, so this is the N, this is south. If you remember Lenz's law, guys, when the magnet is going into the coil, it actually produces a temporary north pole here and a temporary south pole here, right? This is because Lenz's law states that the motion producing the current always opposes the motion producing it. Sorry, let me repeat this again. Lenz's law states that the current always opposes the motion producing it. So if I'm going in here, the only way to oppose my north is to create a temporary north here, yeah guys. Alright, then after that, the first question, what do they want? The coil is connected to the galvanometer. Explain why the galvanometer deflects as the bar magnet is being inserted into the coil. So basically, you have to understand what is going on here. As you insert the bar magnet here, this causes the magnetic field in the bar magnet to cut through this coil, right? When magnetic field is cutting through this coil, current will be flowing here. And when there is current flowing here, it will produce a temporary north and temporary south as well. So you're supposed to understand this before you answer these kind of questions here. So if I were to structure this, I'll say something like magnetic field from the bar magnet cuts through the coils of the solenoid. Alright, cuts through the coils of the solenoid, inducing EMF in the coil, which produces current in the coil. Okay, you're supposed to mention this. Magnetic field from the bar magnet cuts through the coils in the solenoid, inducing EMF, electromotive force in the coil, which ultimately produces current in the coil here. Alright, so this is supposed to be your answer. Then after that, the next question here, what do they want? Explain what determines the direction of the reading of the galvanometer. This one here, obviously, it is purely dependent on the motion of the magnet, right? For example, today if I'm going in here, if this is the north part, it will produce a north and south here, and the current will be upwards. Maybe it will deflect towards the right. if my magnet is moving backwards here, what's going to happen is this will create a temporary south and a north mark, because yet again Lenz's law states that the current produced will always oppose the motion producing it. When you're coming in, I'll repel you. When you're going out, I'll try to attract you backwards, right? So if just now it was deflecting towards the right, right now it will be deflecting towards the left. So you're supposed to answer that. You're supposed to answer something like this. The motion of the magnet determines the direction of the current, which the direction of the reading of the galvanometer, the direction of the reading of the galvanometer. Lenz's law states that the current induced always opposes the motion producing it. Okay, so this is what you're supposed to answer to get your 2 marks, guys. Okay, and finally the last question here, they ask you describe a method for demagnetizing a bar magnet. There are mainly 3 methods of demagnetizing a bar magnet, right? Either you hammer it, or you heat it, or you're going to withdraw it slowly from an AC solenoid, right? So from here I'll just say that place the magnet in an AC solenoid and withdraw it slowly before switching off the current. Alright, these are the quite standard steps to demagnetize a magnet. You should know this by now. Alright, and moving on to this next question here. Figure 9.1 shows a horizontal wire PQ placed in the gap between N pole and the south pole. There is a current in the wire going from P to Q. So if there is a current, and I know for a fact that the magnetic field is going from left to right, this is supposed to be using your Fleming's left-hand rule, because Fleming's left-hand rule is the one that determines the force induced in the current. But let's look at what the question wants. There is a current in the wire and PQ, a force acts on the current carrying wire in the magnetic field. On figure 9.1, draw an arrow to label M to show the direction of the magnetic field in the gap between the poles of the magnet. The direction of the magnetic field is obviously going from north to south, right? So you just label this M. Then after that, an arrow labeled F to show the direction of the force on the current carrying wire due to the magnetic field. Now guys, you're supposed to use the Fleming's left-hand rule here, and for those who are watching online, you may see that this is my right hand on the camera. Is because the camera, Zoom's camera, actually inverts it, guys. Always remember that you're supposed to use the Fleming's left-hand rule, and if you use the Fleming's left-hand rule, first and foremost, you clench your hand into a fist. You always point the direction of the magnetic field. Looking at this direction here, obviously is going from north to south, right? So you should be pointing towards your right. Then once you have your magnetic field pointing towards your right, you should open up your middle finger. You should open up your middle finger with the same position now, where you're supposed to point the direction of your middle finger into the screen. And once you have these 2 positions, your index finger pointing towards the right, your middle finger pointing into the screen, you open up your final finger and you'll notice that the force finger actually goes downwards like this. So this is where you're supposed to be, guys. Make sure you know how to use your Fleming's left-hand rule. Alright, so your force finger should definitely 100% be downwards here. Then after that, the next question, what do they want from you? State the effects of reversing the direction of the current in the wire P. If you reverse the direction of the current and your magnetic field is pointing still the same using a Fleming's left-hand rule, index finger towards the right, your middle finger will be pointing towards you now, right? Your middle finger should be pointing towards you, or something like this, right? Then after that, finally, you're supposed to have your thumb going upwards. Obviously, what's going to happen is the force will be reversed, right? So you're going to say something like, the force acting on the wire is reversed reversed, upwards. Right, it will be obviously pointing upwards at this point. Then finally, the last page here, the magnet is removed and the horizontal current carrying in the wire is left on its own, as shown in figure 9.2. Figure 9.2 sketch the pattern of the magnetic field due to your current in the wire. Now, if you are looking for the magnetic field due to the current in your wire, you're actually supposed to use the right hand grip rule, guys. Right hand, guys. Don't look at the screen and see that this is the left hand. You're actually supposed to use the right hand grip rule here, and using this thumb that indicates the direction of your current, you're supposed to be pointing inwards, and you'll see that your four fingers are actually rotating in the clockwise direction, right? So what you're expected to do is you're actually supposed to draw three circular direction, clockwise direction magnetic fields, right? And you're supposed to label them in the clockwise direction, yeah. So this is what you're supposed to be drawing. And after that, state that if the current in the wire, the current in PQ is increased, state the effects of changing the current in the magnetic field. Obviously, what's going to happen is you'll have a stronger magnetic field, stronger magnetic field induced. Because you have a stronger current, it means to say you'll have a stronger magnetic field. And finally, a small magnet is placed at a point where the magnetic field is vertically upwards. State the direction of the force on the S pole of this magnet. So this question here, a lot of students, they always get it wrong, or they kind of think that is related to this question here. But I can tell you that it is actually a question of its own now. If you look at the information here, it starts off with saying that the magnetic field is going directly upwards, right? If the magnetic field is going directly upwards here, it means to say this is supposed to be the north. This is supposed to be the north pole, and this is supposed to be the south pole, right? Then they ask you to state the direction of the force of the S pole. Obviously, this S pole will be attracted downwards. So, in this answer, you're just going to say that S pole is attracted downwards. And this is going to be your answer for this question here. A lot of times, even I have done this mistake as well. I thought that there will be a magnetic field here going upwards, and then there will be a south pole here, right? Then I even told them that the force will be going towards the right, because I thought that it was related to the question on top. But it is actually not. It is a question of its own. You can refer to the mark scheme to check this answer as well. Alright, so that's that. Looking at the next set of exercise here. What do they want from you? The current in the coil produces a magnetic field around it as shown. The magnitude of the potential difference across the coil is increased and its direction is reversed. So just now it's pointing this direction. If you reverse, then obviously it's pointing this direction here. But because it has a greater potential difference, it'll obviously have a stronger magnetic field as well. State what happens to the magnetic field. The lines become closer together and the right hand end becomes the south pole. Okay, this is logical. The lines become closer together and the right hand remains the north pole. Illogical. The line becomes further apart. Not further apart, they're stronger, becomes further apart. No. The lines become closer together because they are denser right now. The stronger magnetic field is going to cause the magnetic field to become denser. Yeah. Then after that, the diagram shows a current carrying conductor in the magnetic field, which arrow shows the direction of the force acting on the conductor. So if my current is going in this direction here, yet again you're looking for force, so you're supposed to use the Fleming's left hand rule. First and foremost, you clench your hand into a fist, you point the magnetic field towards the left, right, because it's obviously going from left to right, from right to left, right. So from here, then after that, they said that the current is going inwards, right? If your current is going inwards, your force finger should be in the upwards direction. Your force finger should be in the upwards direction. It will look something like this. Magnetic field towards the left, current finger into the screen, and finally your force finger will be upwards here. Always clench your hand into a fist before you do everything. Then going to the next question, in an AC generator, a coil is rotated in the magnetic field and an EMF is induced in the coil. In which position of the coil does the EMF has the largest value? This is basically a AC generator, right? And AC generators will produce the greatest magnetic field when they are cutting perpendicularly against the magnetic field, right? This here will be the maximum. This at this instance here, it is moving parallel with the magnetic field, right? So this is the minimal. Everything else is in between. So A is the obvious answer in this question here. And moving on to the next question, the wire P carries a current directly perpendicular into the page. It is current carrying into the page. A compass is placed at point Q. The compass will be placed here, which is close to point P. The magnetic field at Q due to the current is very much larger than the magnetic field of the Earth. In which direction does the north pole of the compass point? Now basically they're saying that the current here, the magnetic field due to P is much greater than the magnetic field of the Earth, right, which is affecting the compass. So first and foremost, you should understand that if the current is going into the page, you're using your right hand grip rule again, and you see that your four fingers are rotating in the clockwise direction. If your magnetic field is in the clockwise direction, the only logical answer here is going to be A, because you can kind of imagine like the magnetic field is in this direction, right? In this direction here. So your only logical answer which is affecting the compass is going to be A. Because always remember, guys, a compass is a weak magnet. The weak magnet will always be affected by the stronger magnetic field. Right, so your answer is definitely going to be A here. Then finally, for ABC part, the solenoid is connected to a battery. The current is flowing in this direction. Which statement about the magnetic field at the center of the solenoid is correct? The center of the solenoid, which is this part here. You should understand that the magnetic field does not stop only at the edges here. They actually continue inside as well. So first one, he says that magnetic field along the axis is 0. It's impossible. There will be magnetic field here as well. The direction of the magnetic field is at an angle of 45 degrees. I don't know why would this be correct. The direction of the magnetic field is parallel to the axis. Absolutely true, because the magnetic field should be inside. It actually continues inwards. You can refer to the notes from 4.1 as well, guys. Alright. And finally, moving on to the next part here. Figure 10.1 shows a straight wire AB placed in a magnetic field between the poles of the magnet. The ends of ABs are connected to a galvanometer. When AB is moved vertically up and down, obviously, the needle of the galvanometer starts deflecting. Right? State 3 factors that affect the size of the deflection. Now, there are 3 main factors that affect the size of deflection in the galvanometer. Number 1 is obviously the strength of the magnet. Right, the stronger the magnet, the more magnetic field there will be. So when it cuts through the coil, it will produce more current. And the second one will obviously be the speed of the wire be cutting through the coil, the magnetic field. The faster you cut the magnetic field, the more current will be induced. And the final one here is supposed to be the number of turns in the coil. But since this one here, there's not a lot of number of turns, you could say that the length of AB, which is within the magnetic field, the length of wire AB, which is within the magnetic field. Meaning to say, if there's more length of the wire cutting through the magnetic field, like let's say for example here to here cutting through the magnetic field, or here to here cutting through the magnetic field, or here to here cutting through the magnetic field, the more length of the wire in the magnetic field, more current will be induced as well. So these are your 3 standard answers here, right? And moving on to the next question. A student wants to demagnetize a permanent bar magnet. She suggests these steps here. Place the magnet in a long coil, switch on the alternating current in the coil, switch off the alternating of the coil. You're not supposed to switch it off, or you're supposed to leave the current on first, or remove the bar from the coil. Yeah. So this is the only step that is wrong. State and explain whether these steps will always be able to demagnetize the magnet. Answer is a definite no. Then you're supposed to explain why. The current of the coil should remain on. Maybe I'll write the full sentence. How do I write this full sentence here? The current, the bar magnet should be slowly withdrawn from the coil before the current is switched off to demagnetize. Demagnetize the magnet. Yeah, so basically you're supposed to switch. You're not supposed to switch it off first, or you're supposed to leave the current on, then only slowly withdraw it before you're switching it off. No, the bar magnet should be slowly withdrawn from the coil before the current is switched off to demagnetize the magnet. Yeah. So this is going to be your answer here. And moving on to the next question. Figure 9.1 shows a coil supplied with current using a split ring commutator. This is obviously a DC motor here, right? State and explain any motion of the coil. Obviously, what's going to happen is when the current is flowing in here, the current inside here produces its own magnetic field, right, which will interact with the permanent magnetic field here, and thus producing a force on either both sides. So if I'm supposed to structure this, I'll say something like the coil starts rotating 360 degrees. This is because the current in the coil produces its own magnetic field in the coil, which interacts with the magnetic field from the permanent magnet. This causes a force to be generated on both causes a two opposite forces to be generated on both the coil, spinning it in. Yeah, this is supposed to be your answer. The coil starts rotating 360 degrees because the current in the coil produces its own magnetic field in the coil, which interacts with the magnetic field from the permanent magnet. This causes two opposite forces to be generated on the coil. So one will either go up and one will either go down, right? I'm supposed to mention which direction is it going to be. Let me see. With the current, this is going to be your Fleming's left-hand rule again. Looking at this part of the coil here, the magnetic field is going kind of upwards. The current will be coming downwards here, right? Then after that, your force will be upwards. So it's actually going to rotate in the clockwise direction. Rotating the coil in the clockwise direction. Okay, let's add one more part here. Rotating the coil in a clockwise direction here. Okay, just use your Fleming's left-hand rule. For either side of the coil is acceptable as well. Okay, then after that, moving on to the next part here. The coil in 9.1 consists of 3 turns of the wire. The magnetic field strength is M with a current of 2 amperes here in the coil. The coil experiences a turning effect T. The first row shows table 9.1 of data, 3 number of turns, 2 current, M gives a rotating coil here. Complete table 9.1 to give the turning effects of the changes made to the arrangement shown in figure 9.1. Choose your answer from the box. So looking at this next box here, everything stayed the same except for this one, it was a multiple of 4. So obviously the turning effect is going to be 4 times as well lah. Now after that, the next one here, this was the same, this was the same, this here to here changed to a multiple of 2. So yet again, the multiplication is going to be 2 times the turning effect. And finally, the last one here, this was the same, this was the same, this one here divided by 2. So obviously the turning effect divided by 2 as well. So your answer should be 4T, 2T, and T over 2 here. Alright. Moving on to the next question here. Figure 9.1 shows a coil AB with 2 turns. The coil is in the magnetic field. When there is a current in the coil experiences a turning effect. Explain why there is a turning effect once again, and this time you see that it is only 1 mark here. The long answer is because there is current here which produces its own magnetic field which interacts with the permanent magnet's magnetic field and generates a force upwards and downwards here lah, right? But in this question here, you don't have to answer that because it is only 1 mark. You're supposed to just say that force is generated on the coil due to the interaction of the magnetic field from the coil and permanent magnet. Okay, then that's good enough already because it is only 1 mark. Right. Then moving on to the next part here, which is very similar to the previous question. A value of current is 3 amperes. Place 1 tick to indicate how the turning effects changes with the change described. Oh, the keyword here is that initially it had 2 turns as well. So it had initial 2 turns, it had 3 amperes, and the strength of the magnet was originally M lah, right? So if they say that the turn increases to 6 here, here to here is a multiple of 3, right? So obviously it increases by a factor of 3 here. Here to here is a multiple of 3 again. So yet again it increases to a factor of 3. Strength decreases by a factor of 2. So obviously the turning effect decreases by a factor of 2 as well. Quite straightforward, nothing much to explain here, right? Moving on to the next part, which is almost the final part here. Figure 9.1 shows the magnet held just below a vertical coil connected to a galvanometer. The magnet is released, so it's going to produce a temporary south and a temporary north here. State any effects on the galvanometer. Obviously what's going to happen is the galvanometer will deflect momentarily and then return to position 0. Why will it return to position 0? Because this is just one motion, right? It will produce a current for a while, then after that it will return back to position 0 here. Alright, and after that, state any effects on the magnetic field produced by the coil. Obviously there will be magnetic field lah, right? As the magnet is dropping away, right? Lenz's law states that the current induced always opposes the motion producing it, so it produces this temporary north and temporary south law, right? So if I were to write this down, I'll say something like the coil produces a temporary south pole. What was it? South pole? Yeah, south pole at the bottom of the coil. This is in line with Lenz's law, which states that current opposes the motion producing. Okay, this is supposed to be your answer. And finally, the last question here. A bar magnet is held with its end pole just inside one of the coil. Figure 10.1 shows the coil connected to the galvanometer with a 0 mark in the center of the scale here. The magnet is pulled horizontally towards the right at constant speed through a large distance. So if this is the north and it's pulled towards the right, it will produce a temporary south and a north here, right? State what happens to the galvanometer reading as time passes. Yet again, is a similar question, right? You're going to say that the galvanometer deflects momentarily and returns to position 0. Right? In fact, it's the exact same answer here. As the magnet moves and north pole is produced on the left of the coil, explain why the pole on the L is going to be the north pole. It's the same question lah. Basically, you're supposed to say that Lenz's law states that the current in the coil opposes the motion producing it. So it produces a south on the right of the coil to oppose the right motion of the magnet. Okay, you're supposed to write something like this here. Okay. Okay, guys, moving on to the final exercise for this chapter here. Question number 1, a current carrying coil is placed in a magnetic field which affects the coil experience. Obviously, if it is in the magnetic field and there is current flowing in this coil here, there is definitely going to be force exerted upwards and downwards onto this coil, right? So because of that, it will cause a turning effect, and thus your answer is going to be D here. Then after that, second question here, what is the purpose of a commutator in a DC motor? Like I've mentioned, split ring commutators reverse the direction of current every 180 degrees so that the coil can rotate in 360 degrees, right? You just see which one is more closely worded that way, right? To control the speed at which the motor rotates is definitely not true. To reverse the direction of voltage across the power supply every half turn, this could be possible, but obviously current would be better. To reverse the direction of current in the coil every half turn, this sounds more logical. To reverse the direction of the spin, definitely not logical. So C is the only answer here, yeah, guys. Then moving on to the next part here. The diagram shows a wire between two magnetic poles. The wire is connected in a circuit with an ammeter. The wire is moved downwards towards the bottom of the page. A current is induced in this wire here. First and foremost, this part here, we have to find out where is the current induced. Using your Fleming's left hand, again, clench it into a fist, point it towards the right, and your wire is moved downwards here. Or sorry, this one here is supposed to use the Fleming's right hand rule instead, because you're looking for the current, right? Your right hand is always looking for the current. Yet again, clench it into a fist, point it towards the right, and your force pointing downwards will have your current. For those who cannot see, you'll have your current pointing inwards. Meaning to say, when you force this wire downwards, there will be a current that flows in this specific direction here. In which direction is the force on the wire caused by the current here? Now today, if I want to find the force on the wire based on the current, because the current is coming downwards, right? And from here, if you use your right hand grip rule, you'll see that the magnetic field produced due to this current is going to be in a anti-clockwise direction, right? Today, if I were to draw the cross-section area of this thing, the north pole will be here, the south pole will be here. Because the current is coming inwards, right, you'll have a magnetic field that is going to go in this clockwise direction. And if you have a magnetic field in this clockwise direction here, the magnetic field generated will actually push, it will actually push this coil upwards here instead, because you have to follow the roundabout, right? So from here, D is going to be the answer. Now this question here is a little bit tricky because it involves two parts. The first part, you have to find the current, the direction of the current generated in your coil. The second part, you need to find out which direction is the force. Even though this here is being pushed downwards, according to Lenz's law, which states that the current always opposes the motion producing it, right? That's why you will always have a resultant force that is supposed to be pushing upwards here, even though you're pushing downwards. This also explains why when you generate current in the coil, every time we push downward, it feels like there is a motion opposing you. That motion is due to the Lenz's law effect. and thus D should be your answer here, guys. Alright, so from here the diagram shows a current carrying wire placed between the two magnetic poles. The current in the coil is shown as current here. What is the direction of the force on the wire here? If you're looking for force, you're supposed to use the Fleming's left hand rule. Magnetic field towards the left, current coming towards you out of the screen, right? And thus your force should be downwards. If you're looking for the force downwards, it should be towards the bottom of the page, and thus A is the answer here. Then question number 5. The diagram shows a AC generator. The coil is turning as shown. The diagram shows the output voltage by the generator as the coil turns. Which point on the diagram 2 shows the voltage induced in this coil when moving through the position shown in diagram 1? Now at this position here, you can see that the coil at this instance is actually moving parallel with the magnetic field. If it's moving parallel with the magnetic field, obviously the current generated and voltage generated should be at the minimum. So B should be the answer here, guys. Alright, then final question for the ABC. A conductor carrying a current is placed in the magnetic field. In which direction does the force on the conductor act on? If there's a current here, you're supposed to find the force using a Fleming's left hand rule again, yet again. Magnetic field pointing towards the right. Then after that, your current will be pointing out of the screen. It's supposed to be pointing out of the screen, and thus your force finger should be pointing upwards here. And thus A should be your answer. Alright. And moving on to the paper 4 question, a student turns the handle of an alternating generator and the coil rotates. Figure 8.1 represents the structure of the AC generator here. There is an alternating voltage output between the two terminals. Explain why rotating the coil produces an output voltage. Now this here is basically talking about electromagnetic induction, right, which states that the coil cutting through this magnetic field will generate its own EMF and ultimately inducing current flowing in this coil here. So if I were to structure this, I would say something like, as the coil rotates, it cuts through the magnetic field from the magnet, inducing an EMF in the coil, ultimately producing an alternating current in the coil. Alright, whenever you ask about these kind of questions here, always remember that you're supposed to answer it in terms of the electromagnetic induction procedure here, guys. Always the keyword here is the magnetic field being cut. As long as you cut through the magnetic field, it will generate EMF first, then current will be flowing in the coil. Okay, so this is your standard answer here. Then moving on to the next part, state the position of the rotating coil when the alternating voltage is at maximum value and explain why the maximum output occurs at this position here. The maximum value will be generated when the coil cuts through perpendicularly against the magnetic field. So if I were to word this, I'll say that the coil must be in a horizontal position. The reason why it generates the maximum is because at this instance it cuts through the magnetic field perpendicularly, which generates the maximum current here. So I'm going to say that the coil should be in the horizontal position because it will cut through the magnetic field perpendicularly. Oh, how do you spell perpendicularly? Inducing the largest current. Okay, this is what you're supposed to mention. Alright. Then after that, moving on to the next part here, a lamp and an open switch are connected in series to the output terminal AC generator. The switch is closed and the lamp lights up. The student has to apply a greater force on the handle. Explain why a greater force is needed to keep the lamp open. This here is basically talking about what's it called, the Lenz's law again, right? And Lenz's law states that the current induced in the coil always opposes the motion producing it, right? Meaning to say, when I go upwards here, I'll have an opposing motion, opposing force that is kind of going downwards here. That's why you can feel that there is a greater force needed to generate the current, right? So we're basically supposed to answer this in terms of Lenz's law, right? So Lenz's law states that induced current due to electromagnetic induction always opposes the motion producing it. The current in the coil produces an opposing motion due to the interaction between the magnetic fields. Okay, supposed to mention something like this lah. And finally, to the last part here, no, not the last part, second last part here, describe how to demagnetize a bar magnet using an alternating current in the coil. This is quite a standard question with a very standard answer. You're basically supposed to place a bar magnet in a solenoid carrying alternating current and slowly withdraw the bar magnet out of the coils before turning off the current. This way it will definitely demagnetize the bar magnet. It's quite a standard question. You see this a lot in your paper 2 as well, yeah, guys. Alright. And moving on, figure 9.1 shows a simple DC motor. Explain the purpose of a split ring commutator. Now I've mentioned this many times in class already. A split ring commutator basically reverses the direction of the current every 180 degrees turn of the coil so that the coil can continuously spin in a 360 degree motion. Alright, so structure this here. You can say that split ring commutators reverses the direction of the current in the coil every 180 degrees so that the coil is able to continuously spin 360 degrees. Okay, and this is what is going to give you your 3 marks here. And final question for this part here. The voltage of the power supply is increased. State the effect of this on the motor here. Obviously, when you have more current or voltage, then the motor is going to spin faster lah. The motor spins faster. It is the same concept of how your fan works on power on rotation 1, 2, and 3. It's basically just providing more current to the coil so that it is able to spin faster. Alright. Then the final question here, figure 10.1 shows a simple alternating current generator. On figure 10.2, sketch a graph to show how the electromotive force induced varies with the time for one revolution of the coil. Assume that the coil starts at the horizontal position as shown here. Label the points on the time axis where the coil has completed a quarter of the revolution and 3/4 of the revolution here. Now, if the coil is starting at a horizontal position, at this instance here, it actually moves perpendicularly against the magnetic field, right? And if it's moving perpendicularly against the magnetic field, what's going to happen is EMF will be at the maximum here. Then EMF will start to drop here and then come back here, right? Every quarter rotation means to say 90 degrees. If I were to draw the cross-sectional area being this north and south here right now, at this instance the coil is at a horizontal motion, right? When the coil is at the perpendicular motion, this is basically 90 degrees turn, which is also equivalent to a quarter of the revolution, right? Because at this instance here it is moving parallel with the magnetic field, it will actually generate the least amount of current. So here is going to be 1/4. Same thing for 3/4 as well. It will be moving parallel with the magnetic field, and thus you'll have something like this here. Okay. Then after that, explain why an EMF is induced only when the coil is turning. Obviously, because when the coil is turning, the coil cuts through the magnetic field, right? because it cuts through the magnetic field, then obviously it's going to start generating some current, right? State the name of the component PQ and state their purposes. PQ is obviously a slip ring here. Slip ring commutator. If you write slip ring, it's good enough as well. If you write commutator, it's better. The purpose is to allow the coil to continuously rotate in 360 degrees even with the current. So if I were to structure this, I'll probably say something like allows 360 degrees rotation without disconnecting the current. Okay, allows 360 degrees rotation without disconnecting the current here. And finally, they ask you for two possible changes that cause the larger EMF to be induced. Obviously, there's three standard ones, right? You spin it faster, you increase the magnetic field strength, or you use more number of turns in the coil, right? Just write either two is acceptable. Alright, using a stronger magnet with greater magnetic field strength, or you could even say spinning the coil faster here, okay, or anything that's logical, right? And that's how you do these questions here.